Okay, I'm going to go through the 9-station review here for Unit 12. So each of the following, write R if we're talking about reduction, O if we're talking about oxidation. Okay, occurs at the anode. Okay, oxidation always occurs at the anode, and you can remember anox, or the fact those are two vowels, O and A. Copper 2 plus, okay, so notice that the charge is going from 2 down to 0, so the charge is reduced, that's reduction, or you can say it's gaining electrons, GER. Gains electrons is reduction. Leo the lion says GER, and GER means gaining electrons is reduction. Charge on the element becomes more negative. Okay, more negative means it's going downward, and so that's reduction. Electrons are on the right side of the arrow. Okay, if it's on the right side of the arrow, then that means that they're losing negatives. It's getting more positive, so that's oxidation. Okay, this is a picture here where here electrons are on the right side. Okay, so we know that that's oxidation. But we can also look at the charge. It's going from -1 up to 0. So it's getting higher up, that's oxidation. Losing electrons is oxidation. So losing electrons, right side of the arrow, those all go together. Here's some electrons on the left side of the arrow, so that's reduction. And you can see the charge on this is 0 and going to -1. So 0 down to -1, that's reduction. Occurs at the cathode. Okay, reduction always occurs at the cathode, and the mnemonic there is red cat, which means reduction at the cathode. Charge on the element becomes more positive. More positive is oxidation. Okay, station 2. So we got some metals, W, X, Y, and Z are inserted into a potato. This is like our lab. And the electrical potential across the metals was measured. This data is recorded. So rank the metals from the highest to lowest. Okay, so whoever is the cathode the most is the one that is highest in the reduction potential table. So if we're looking at here, it looks at, these are all positive, so that's all good stuff. Okay, so who's the cathode? X, W, W, X, X, Y, Z. So Y is never the one, so Y is the lowest one on the reduction potential, and X shows up 3 times, so that's the highest, W is next, and Z is next. So it looks like that. We're not looking at the anodes at all, just the cathodes. The more often it is in the cathode, then the higher up it is in the reduction potential. The more often the metal is the cathode, the higher E0 reduction it has. So the higher up it is in the table, and that's what we're looking for. Okay, station 3, a potato clock. Okay, use the following reduction potentials. Okay, zinc and copper were inserted into the potato. Okay, so looking at this, we're going to say, well, what's going on? Copper electrode, zinc electrode. So of these two, we can see that copper is the higher number, even though it's not higher up in our chart, you know, just listed, it is the higher number. So this one is going to be the reduction. Okay, this is going to be written as is. Okay, this other one, the lower one, that's going to be the oxidation, and that's going to have to be written in reverse. So with that in mind, so the copper electrode, copper is going to be just like we see it up here. So copper 2 plus 2 electrons becomes copper metal. The zinc electrode, we're going to write it in reverse. So the zinc metal arrow is going to turn into zinc 2 plus 2 electrons. So for the zinc, we wrote this on the left, and we wrote this part here on the right. Okay, on the copper, we wrote it just exactly as is. Okay, so on the copper electrode, that is reduction. Okay, it's gaining electrons. Okay, gain, reduce, oxidize, lose, so it's gaining electrons. And since it's reduction, reduction always occurs at the cathode. In the same way over here, okay, this guy is losing electrons. Losing electrons is oxidation, and that oxidation means this is the anode. So reduction always occurs at the cathode, oxidation always occurs at the anode. Okay, something is missing from this picture of the potato clock. What is it? Okay, we can see that we need one more wire. So we have a wire going from the clock to each potato, but we have to finish this off with another wire that goes from this potato over to this potato. Okay, and if let's say this side was zinc, then this side would be copper. If that was copper, this would be zinc, and then this would be copper. So we'd have to have the various copper and zinc in each of the potatoes to make this work. So what's missing? The wire between the potatoes. Okay, station 4, oxidation and reduction. Which of these ions is most likely to get to be reduced? Okay, so these are written in order, so that's good. And so which is most likely? Well, the highest one up is the most likely to get reduced, so it's the Ag+. So whoever's up here, that's the most likely to get reduced. Who's most likely to get oxidized? The bottom right. So this for these three, the lead metal is the most likely to get oxidized. So consider this oxidation reduction reaction, copper plus lead, lead plus copper. Write the reduction half reaction. So who's getting reduced? Copper 2 plus to copper 0. So copper 2 plus, it's going to pick up 2 electrons, become copper 0. Write the oxidation half reaction. Okay, well, we can see lead is turning into lead 2 plus. So Pb0, okay, turns into Pb2 plus. And it does that by losing 2 electrons. Calculate the voltage, okay, created by this redox. Okay, so the voltage for the lead, because we turned it around, then we're going to say now its oxidation potential equals positive 0.13 volts. And the copper as is E0 reduction, and that is positive 0.34 volts. So we're using this number just as is. Okay, this number we had to change the sign because it's going in reverse. And to get the voltage of the cell, we just add these two together. So the E of the cell is equal to the reduction potential plus the oxidation potential, which in this case is positive 0.34 volts plus positive 0.13 volts. And so that comes out to be 0.47 volts, positive 0.47 volts. Okay, station 5, redox equation. Consider the following half reactions and E0 values. An electrochemical cell setup. Write the equations for the reactions at each electrode and the overall. Calculate the value of the cell. Okay, so we're looking at this and we say, okay, who is the higher number? This is the higher number. Because that's a higher number, this is reduction, and it happens at the cathode. So just knowing by the numbers, that's going to be, so let's write this down. The cathode equation is Ag plus an electron becomes Ag neutral, and the voltage associated with that is positive 0.80 volts. Okay, this other guy here, the lower of the two numbers, then it's going to have to go in reverse, so that is going to be oxidation. Okay, and that's going to happen at the anode. And so the anode reaction is written this backwards. Copper metal turns into copper 2 plus and 2 electrons. And the voltage associated with that, because we have turned it around, now the voltage is negative 0.34 volts. Okay, so first off, what's the overall reaction and what's the overall voltage? Well, let's do the voltage first. So 0.8 minus 0.34, that is going to be positive 0.46 volts. Now notice we just do those numbers, take those numbers and do them right away. Don't mess with them. Okay, over here we're going to put these together, and to put these together we need the electrons to cancel. So we need to double this reaction. Okay, so 2 electrons, they cancel. So the overall reaction, I'm going to write it down here because I have more room, is 2Ag plus Cu neutral turns into Cu2 plus 2Ag neutral. Okay, so that's my overall reaction. But notice, even though I doubled the silver, I did not double my voltage, because the voltage is already taken into account how many electrons are transferred. So we just have to use those numbers as is right off the chart to get this voltage. Okay, number 6. Okay, write the equations for the reactions at each electrode and for the overall reaction. Okay, so we're just doing the same thing we did before. So tin and zinc, let's find those. Okay, so SN and ZN. So here's tin and here is zinc. Okay, so first off, the voltage is going to be, okay, the higher one, and this is from high to low. Okay, so the voltage is going to be negative 0.14 plus, we're going to take the other one and turn it around, so it's going to be positive 0.763. So the voltage for that, I get it with my calculator, is 0.623 volts. Okay, write the equations for the reactions at each electrode and the overall. Oof. Okay, I haven't got a lot of room here. I'm only doing it twice. I can fit it in. So for my tin, the higher one, it is going to be the written as written. So there's the reaction as written. So I'm going to write it up here. SN2 plus 2 electrons becomes SN metal, and that is going to happen at the cathode. And then at the anode, then the zinc one, but it's going to be backwards, so it's going to be Zn neutral, turns into Zn2 plus 2 electrons. Okay, so this is on the right, that's on the left. No, this is on the left, this is on the right of my equation. And my overall equation then, I'm going to put these together. I got 2 electrons, I got 2 electrons. So it's a little messy, but I'll write it carefully. So Sn2 plus zinc becomes Zn2 plus Sn. So that's that, and that's the voltage, positive 0.623 volts. Okay, let's try the same thing here with cadmium. Okay, so cadmium and aluminum. So there's aluminum, and there's the cadmium. Okay, so cadmium is higher up, so cadmium is going to be written as is, so Cd2 plus 2 electrons becomes Cd neutral, and its voltage is negative 0.40, and the aluminum is going to be written in reverse, so because it's the lower of the two, so I'm going to put this on the right, so aluminum metal turns into, put this on the left, put this on the right, I keep saying that wrong, Al3 plus 3 electrons. Okay, now that's going to have a voltage of positive 1.66 volts. Okay, I'm going to put those together right now before I do anything else, so I can see that it's going to be positive 1.66 minus 0.4, so it's going to be positive 1.26 volts. That's going to be my voltage. Now I'm going to go back and put these together. Before I put it together, this is 2 electrons and 3 electrons, so I'm going to have to triple this guy, so 3 and 3, and make that a 6. And I'm going to double this guy, 2 and 2, and that'll make that a 6. So my 6 electrons cancel. So my final equation is going to be 3 cadmium 2 plus, 3 cadmium 2 pluses plus 2 aluminum metals turn into 2 aluminum 3 pluses and 3 cadmium metals. So that's my equation, and there's the voltage that goes with it. And notice again, I did not multiply this by 3 and did not multiply that by 2. Those numbers are already taken. We just use them as is off the chart. Okay, we're up to, this is 7. This is a pencil lab, excuse me. The reactions that occur at each pencil are given. Circle the appropriate words for each of the pairs. Okay, so let's do the one on the right over here. And so what's going on? Electrons are on the right, so it's giving off electrons, losing electrons. Okay, losing electrons is oxidation, Leo, the lions of losing electrons, oxidation. Oxidation always occurs at the anode. Okay, at the other side over here, there's electrons are being gained on the left side. So gaining electrons is reduction, Grr. So this is reduction. Reduction always occurs at the cathode. So those are just things we know from the equation. Okay, label the pencil that is connected to the positive end of the battery. Okay, so, oh boy. What role does the battery serve? Okay, the battery serves to pump electrons from the anode to the cathode. So electrons are always traveling from the anode to the cathode. Okay, so label the pencil that is connected to the positive end. Okay, well, oxidation is losing electrons. So the electrons are leaving. Okay, let me think. Okay, oxidation. The chemicals are losing electrons. So the chemicals are going into the pencil because it must be positively charged. So this side must be the positive charge, and this side must be the negative charge. So who's connected to the positive? Okay, this guy is the positive because oxidation occurs. Okay, at the negative side, it's got too many electrons down here because of the battery, so whoever touches it is going to gain electrons. Okay, so that makes sense. So yeah, so the positive pencil, the one on the right. If phenolphthalein indicator were added to the liquid in the petri dish, draw the area that would turn pink. Okay, well, I don't have pink, I have red. I'll use that. Now I have some purple. I'll count purple. Okay, so where would it be? Phenolphthalein turns pink with hydroxide. There's hydroxide. So this side here would be the side that's going to turn pink. Hot pink. Okay? And we should see some bubbles there, hydrogen bubbles. Okay. Draw. We just did. Okay, for number 8, more pencil lab. The pencil placed in a solution of sodium bromide and universal indicator. Remember that acid is red, base is purple. Both the sodium and hot water can be reduced. Circle the half reaction that will take place. What would you observe? Okay, so we're saying sodium and water, and that's going to get reduced. So we're looking at the reduction chart. So we have sodium and we have water. Who is really going to change? It's going to be whichever one has the higher potential. So it certainly is going to be the water. Water is much higher than sodium. Okay, justify your answer. Okay, so what would you observe? Okay, you would observe hydrogen gas bubbles. You wouldn't know they're hydrogen gas, but you would observe bubbles. And because this is hydroxide, okay, then that's going to be a base. Okay, solution will turn purple. Okay, because of the hydroxide. Okay, so those are the observations, and the justification is we're going to get bubbles because we have hydrogen gas formed, and it's going to be purple because we have hydroxides formed. Okay, on the other side here, it says both bromine and water can be oxidized. So let's look at this chart. Circle the half reaction. So bromide, here's bromide. Okay, and water. There's water. Okay, so who's going to change? Well, the higher of the two. So that's one. So the bromine's going to that. So what would you observe? Okay, we would observe bromine formed. Okay, so we might see some kind of a reddish brown color. And I think that's all we're going to see. Okay, so we would just see is just some little bit of color forming over that one. Okay, we're going to form that because we're going to see a red-brown color because we're forming some bromine. Okay. Okay, station 9, redox reactions. Okay, look at this equation, right? The reduction half reaction, the oxidation half reactions, and how many electrons are transferred. Okay, so reduction. Whose charge is going down? So let's look at everybody really quick here, and we'll say, well, sodium, neutral, that's a neutral, so that's got 0 charge. Okay, this guy also has 0 charge, because it's a neutral element. This is +1 charge, and this is -1 charge. So reduction means its charge goes down. Who's getting reduced? 0 to -1. Okay, that's reduction. So it's Cl2 changing to 2 Cl minuses, and the electrons go on the more positive side. We're going to need 2 of them. So gaining electrons is reduction. Grr, that makes sense. Okay, let's do the oxidation. Okay, its charge must go up. Well, it better be the sodium because we haven't used it yet. So this guy is going from 0 to +1. So Na is becoming Na+. And so we're going to put electron on this side. So since it's Na becomes Na plus, we can just do it like this. There's two of them in this equation to balance the two that are lost there. But if we just want to write the half reaction, we can write 2, 2, and 2, or 1, 1, and 1. Either one's great. Okay, how many electrons are transferred? Well, 2 electrons are being transferred here. Okay, this guy, we'd have to double it to make it all balanced. So 2 electrons are balanced. So 2 electrons are transferred. And that is the quick check. No, it's not quick check. That's the 9-station review. Good luck on your test.